When a solid rocket motor ignites, it is just unbelievable force. We're talking about turning thousands of pounds of solid fuel into a controlled explosion, powerful enough to launch huge payloads into orbit. But for decades, there was a hidden danger hiding inside all that fire, an invisible rattle, a vibration so intense it could literally shake the engine to pieces before it even got off the ground. So let's dive into this amazing engineering mystery.
So yeah, that's the big question, right? What invisible force could possibly be powerful enough to do that? We're going to unpack it by looking at some really foundational work by G.A. Flandreau. It's a story that's kind of a scientific detective hunt, searching for a tiny, almost invisible culprit that had the power to destroy our most powerful machines.
All right, so before we get to the solution, you gotta appreciate just how big a deal this problem was. For the early rocket designers, this wasn't just some small annoyance. It was a critical and often catastrophic roadblock. I mean, picture this. You're an engineer. You've built what you think is a perfect engine. Everything looks good on paper. But when you test fire it, the pressure inside starts jumping all over the place, shaking the entire structure with this incredible violence. That was the reality. They knew something was terribly wrong, but the cause? A total mystery, lost in the fiery chaos inside the combustion chamber.
So the scientists realized maybe the problem wasn't with the metal, maybe it was something happening in the gas itself. The clues were pointing away from a structural flaw and towards something being created inside the exhaust flow. And that's when they started hunting for whirlpools.
Okay, so take a look at this. This is kind of like the crime scene, before the crime even happens. Inside a rocket, you've got slower-moving gas coming off the burning propellant along the walls, and it's meeting this super-fast jet of gas roaring down the center. And right where they meet, you get what's called a sheared flow, this zone of really intense turbulence, this unstable boundary. This is the perfect breeding ground for our invisible enemy.
And that brings us to our prime suspect, vortex shedding. The easiest way to picture this is a flag flapping in the wind. As the wind flows past the flagpole, it creates these little whirlpools of air. We call them vortices that just peel off one after the other. Well, the same thing happens inside a rocket with superheated gas, but with way more energy. But here's the thing. Inside a rocket, these aren't just some gentle little eddies. We're talking about tiny, super concentrated packets of rotational energy.
But here's the twist. A single vortex, or even a bunch of random ones, isn't enough to tear a rocket apart. The real trouble starts when these vortices begin, talking to each other. And to the rocket itself. They get caught in a destructive feedback loop.
Now, I know this diagram from Flandreau's paper looks a little intimidating, but it is brilliant. It's the key to the whole thing. This is the engine of destruction. It shows that this isn't just one thing going wrong. It's a vicious cycle where every single step feeds the next one, and it just gets stronger and stronger every time it goes around.
Okay, so let's break this down, because this cycle is everything. It all starts with that turbulent sheared flow making a few random vortices. But, and this is crucial, the rocket chamber itself has a natural sound, a specific acoustic frequency. This sound field acts like a band conductor, telling all those random vortices to form up in a nice, synchronized pattern. Now that they're organized, they create a much bigger, more powerful pressure pulse. This pulse then reinforces the rocket's own sound field, making it louder. And that louder sound travels back to the start and creates even more synchronized vortices. And that just feeds the whole loop all over again. It's exactly like when a microphone gets too close to a speaker, that tiny hum that explodes into a deafening squeal. Same principle. So, for a while, the thinking was that the sound was just coming from these vortices bumping into each other out in the open. But that just didn't explain the sheer power of the vibrations. The real smoking gun, the big aha moment, came when they figured out what happens when these little whirlpools hit a wall. And this right here is the key insight. The sound from vortices just bumping into each other in open space is called quadrupole sound. Think of it as just background chatter. It's not very efficient. But when a vortex slams into a solid surface, it generates something called dipole sound. This is a much more direct and efficient way to transfer energy. This isn't chatter, this is a bang. And that was the real source of all that destructive energy. And this diagram shows us exactly where that bang happens. That spot where the vortices hit is called the impingement surface. It's usually the entrance to the rocket's nozzle. So you have these perfectly timed vortices marching down the chamber, and then bam! They slam into the surface, releasing all their energy at once. This creates those huge pressure waves that just keep supercharging that feedback loop. So figuring this out was a huge breakthrough. Because once you know how it breaks, you can figure out how to stop it.
And the amazing part is the solution wasn't some complicated new part or some extra piece of hardware. It was just a simple, really elegant design rule. And that rule is all built around something called the Struhal number. You'll see it written as S. Now, it sounds complicated, but it's really just a simple ratio. It basically bundles up the three most important things in this whole mess: how fast the gas is going, the shape of the flow where the vortices are born, and the natural sound of the rocket chamber they're listening to. It's the magic formula that predicts if that dangerous feedback loop can even get started. And get this, the rule itself is incredibly simple. Flandreau's work showed that the feedback loop, that destructive conversation, can only really happen in a very specific range of Strausel numbers. If you can design your rocket motor so that the Strausel number always stays above about 0.5, the whole destructive feedback loop just can't get started. The vortices might still be there, but they can't lock in with the acoustics to start that violent shaking.
And that's the real genius here. You don't have to add extra weight or complex dampers. All you have to do is be smarter about the shape on the inside of the rocket. By making the gas flow smoother, especially where it comes off the propellant, you can change the variables in that Struhal equation. You can push the number up into the safe zone, and you can silence that destructive rattle before it ever even begins. So, you see how this whole thing went from being this terrifying, unpredictable mystery that was destroying rockets to a totally manageable, predictable engineering problem. It was a journey from pure mystery to total mastery.
And this quote from Flandreau's paper really nails it. It's that interaction, that conversation between the sound waves and that unstable gas flow. That's what decides everything. It's the conversation that synchronizes the vortices, that turns all that random chaos into a focused, destructive pulse.
So what's the big takeaway here? Why does this all matter? Because by finally understanding this invisible force and boiling all that complex physics down into a simple design rule, this research literally opened the door for us to build bigger, more powerful, and most importantly, much safer and more reliable solid rocket motors.
And that kind of leaves you with one last thing to think about, right? This was one invisible force, one hidden conversation that we learned how to hear and then how to stop. It just makes you wonder what other invisible forces, what other secret feedback loops are humming away right now inside our most advanced technologies, just waiting for us to figure out how to listen.